Okay, let's start with this one. Okay. So today we will have a continuation of our course in data design and analysis of algorithm. And the course actually, Mr. Ruli Sulaiman has prepared the course for the first for the A and B class. This one, but in this case, there are several slides that I have explained last week. So I will just copy paste. So I combine the course of Mr. Sulaiman and the course of Mr. Subakti. So here we go. So we will have this kind of course and some review for our previous understanding. Okay. I'll start with this one. So, and the model objective of this course or this session are, the first one is correctness of algorithm. Well, this is one is the revisit and review of our previous discussion, followed by growth of function and asymptotic notation. I have introduced about the I introduced the asymptotic notation last week with the big O, big omega, big theta, and we will continue to study furtherly today. And some basic math revisited. In this case, well, you will find several common functions that will be used or widely used, whether to solve the problem or to compute the to compute the computation time. And by doing this, normally you will understand how the complexity of merge sorts will be generated. So also I will explain it next week. So we'll start with the review of correctness of algorithm. When the algorithm is correct if for any legal input terminates and produce the desired output. Automatic proof of correctness is not possible, so we have to prove it manually. And there are practical techniques and rigorous formalism that help to reason about the correctness of algorithm. In this case, we will use the course of mathematical discrete. Well, this is this one, the partial and total correctness. I didn't explain it yet. Partial correctness, what does it mean? If there is any legal input given to the algorithm execute, there is a branch. If this point is reached, then this is the desired output. The output is something else. That's the partial correctness. While total correctness, whatever the flow, the workflow of the algorithm, at the end, at this point, at the end, the desired output always achieved. So that's the total correctness. Furthermore, assertion. There is a term about assertion. Well, assertion, I think in object-oriented programming, you have already, maybe for several lecturers, explain about the assertion. And in this case also, there is a term of assertion. What is assertion? To prove partial correctness, we associate a number of assertion statement about, this is the definition, statement about the state of the execution with specific checkpoint in the algorithm. So assertion in here, it's more like checkpoint. We have to check whether it gives correct answer or not, correct output or not. And for the precondition, assertion must be valid before the execution of an algorithm or a subroutine. So whether this is the whole algorithm or a sub-process, small process in the algorithm, has to be correct. It has to be valid. And the post condition, assertion that must be valid after execution of algorithm. It's normal. the basic idea. Okay. And then we have already discussed this one also, loop invariants. So what is invariants? Assertions that are valid anytime they are reached. So last week and previously, and the week before, I explained about the initialization, maintenance, and termination as the checkpoint. To make sure that your program runs correctly, and the output, the desired output, well, it reaches the desired output. It's true prior to the first iteration. So before we iterate the algorithm, well, before we iterate the data, the input, it has to be true. Must be true. Followed by for each iteration. For each iteration, it means that at the end of the current iteration, it must be true also. And at the end, termination, when loop terminates, the invariant gives a useful property to show the correctness of the algorithm. So at the end, well, it must be true, absolutely. And this is the same example. No, it's a little bit different. Sorry, but it's the same example of loop invariance. Well, we already proved it last week. This is another. This is for sorting. I think for sorting the initial statement, etc. equal to, etc. It has to be sorted. So the sub array over here, it has to be sorted in certain way. Okay, I think we will pass this one. Why? Because there is time we will discuss about the case study, some case study that proposed by Mr. Sulaiman, and I found it very interesting. It's challenging also. So this one, for me, it's better to explain through this one. I think it's easy to understand than I explain it through the file directly. So this is the simple explanation about asymptotic analysis, like rounding. So you make an approximation and rounding. The goal is to simplify analysis of running time by getting rid of details. So we don't need to we don't need to take into account the details, which is not well for small case it matters, but for large, medium, large cases it doesn't matter, which may be affected by specific implementation and hardware. This is more the purpose. So it's like rounding. If we have 1,000,001 or 1,135, for example, we can put its equivalent or like this likely like 1 million. Well, it depends on the how many rounds you want. Maybe you want to round. In general, after comma, you want to put only one character. One character, two character, etc. And this is equivalent like 3n square equivalent to n square. So we don't need to take into account the constant c over here, which is 3. Why? Because it matters only for the small input and we didn't count it well. We don't need to count it very specific. It's not worth it. Capturing the essence, how the running time of an algorithm increases with the size of the input in the limit. So this, yes, you have any question? Andimas, I think. No? Okay.
No, sir.
Okay. So the purpose of asymptotic analysis is to capture the essence, this one, running time, to measure the running time of algorithm increases with the size of input in the limit. Asymptotically, more efficient algorithms are best for all but small input. So best for all except for small input. This one is the small definition of small input. 1, 2, 3. Well, I don't know what's the limit. Depends on the function, actually. And for asymptotic notation, we have, well, last week and previously, I explained that there are three, which are big omega, big theta, and big O. And here, and based on the book, we will, I will explain 5. With the rest is are the little O and little omega. So we start with the big O notation, asymptotic upper bound. So this is the upper bound. What does it mean? Fn equal to big O Gn if there exists constants C and N0 starting point. And this one statement, Fn is less than or equal to C multiplied by Gn. You see over here, the C is the constant, which is in here is 3, but in here it depends on the case. Well, it depends on the computation. For n less than or equal, greater than or equal n0, n0 is over here. So this is the limit of the small input. After small input, then this is the n0 until the end. And here is the function of n, fn. And this one is the big O notation. Sorry, there's an interruption. So see, sorry, what in minute. Okay, let's continue. So this is a function of fn, and this is constanta multiplied by gn. How to say about this? Fn is like an element of big O gn. You can call it like this. Well, we'll find out later. And fn and gn are functions over non-negative integer. Just to make sure that because this is running time, the value is always positive. So this is, well, not positive, non-negative, sorry. Why? Because 0 is possible. Used for worst case analysis. So this is for worst case analysis and widely used. Actually, when the first book, the first or second chapter, first and second chapter of Introduction to Algorithm, consider like big theta. Actually, some cases it's more like big O. So in the real world, we talk mostly about the big O. When we compute, etc., compare, we talk about big O. The second one, after the upper bound, this one is the lower bound. I think it's easy to understand through the image over here. So Fn is the element of big omega, is element of a set of big omega Gn. If there exists constant C and 0, such that C constant Cgn is less or equal Fn for n greater than n0, greater or equal than n0. So from here, in here we didn't take into account because small input, and it's not this one is not, well, because it's small input doesn't give significant differences between the running time. That's why we consider over here. Used to describe best case running times or lower bounds of algorithmic problems. The lower bound is of searching in an unsorted array is big omega n. This is the example. As you can see, when we are looking for an element in an array with the size of n, we'll visit it one by one, and the worst case. What's the worst case? The worst case is when we found out the the element at the end of the array, or it doesn't exist in the array. It's not exist in the array. So that's the well, this one is the lower bound of searching. Unsorted and big O, it's the same thing. I think it's the same thing. So it's n. We have to visit one by one. We have to check it all the possibilities. And asymptotic notation, that simple rule, drop lower order terms and constant factor. So the rule to calculate the asymptotic notation is we have to drop the lower order terms and constant factor. As you can see over here, or if you remember what I said previously, imagine you have a polynomial function or equation, and then you have to drop the lower order terms and only consider the highest. Plus, you have to drop also the constant factor. For example, over here, we have to drop this one. But sir, 50 is very big. Yes, even though this one is like 100, 1,000, 1 million, we don't consider the constant. Why? Because the constant is what to say? It's determined, or it's easy to compute. It's stated. Well, n and n log n over here is uncertain. It depends on the size of the n, and it depends on the length of the input, etc. So we have to consider the dynamic variable, which is n log n. Sir, why we need to consider log n? Why you don't need to consider n? You see over here, this is n multiplied by log n. You have to pay attention with this because it gives a big impact. While over here, it's only plus. If you run your computer if you run a program with your computer which has like parallel processor, multiple processor, normally this one and this one will be calculated simultaneously and in the same time, parallel. So that's why, furthermore, and we have to understand the maximum reach or the maximum needs of resources. So that's why we consider only the highest term, the highest order term. This one is n log n, so we consider only this one. This one is only n, so we drop this one constant and this one constant. Okay, we got n. For this one, we got n square log n. As you can see, this n square multiplied by log n plus 5n square plus n. So we drop this one and we drop this one. So, and this one is big O. Even though this one, I explained it. So this is the approximation or asymptotic approach we talked about. Continue with this one. If we plot or if we draw the function of fn, gn, and constant 1, second constant. So we can see over here, this one is lower bound and this one is upper bound. And this, the big theta and big omega, normally asymptotically tight bound. What does it mean? It means that whenever we expand the number of input size, it will follow the fn function. Well, it follows the pattern of fn function. Like over here, it will, if it will increase, well, it will increase, but shortly and very tight, it's near with the fn, as well as the gn or the big O, the upper bound. It follows the rule. It follows the function. That's why we call it big theta over here and big theta over here, big omega over here, and big O over here. Asymptotically tight bound here, and fn is equal to equal to big theta Gn if there exists constant C1, C2, or N0 such that C1, Gn, you can see over here, the definition of big theta is C1 Gn is less than or equal to Fn, and less than Fn less than or equal to C2 Gn for n greater or equal to N0. If only if Fn is part of big O and Fn is part of big omega, as you can see here, it's the part of between both of them. Fn is misused instead of over here. You see, big O is often misused instead of big theta. So as you can see in the second chapter last week, they write it big theta, but actually it's more like big O. And this is two more asymptotic notations. Little o for here. Notation Fn, you see it's small o, the lowercase of O. Non-typed analog of big O. Non-typed, it means that it has a wide gap and it becomes wider and wider as within the increasing size of n. For every z, there should exist n0 such that Fn, this is the same explanation as previously. If we see over here, no, this one is big omega. This one. So big O is more like big omega. No, because little o is more like big O, but this one, the formula, definition formula is quite similar, and it's used for comparison of running time Fn. This one, because it said that Gn dominates Fn. What does it mean? What does it means by dominates? I will show it. I will show you later with this one. Little omega notation Fn, little omega Gn, non-typed analog of big omega. So this is the contrary of little o, where little o will have the higher or wider distance between Fn and the little o function, which is Gn. But in little omega, it has the low, it will give a wider distance, but in the lower bound with the small theta, little omega notation. Is there any little theta? No. Why? Because actually we consider little theta, obviously it's within this one, and this is the definition of big theta. So we don't need to explain it again. And this is for me, it's easier to understand about the little o by doing this. So we meet again calculus. Limit n approximation to infinity, Fn Gn equal to 0. So this is the basic foundation of little o. If we can see over here, the big O n is over here, the upper bound, but it still follow the rule or follow the function of the, similar to Fn. So we call it tightly related, big O with big theta. While big omega, it's similar with big O, it has tight relation over here, distance. In the other hand, this one, big little o, you see over here, it will create a very, very wide distance, and it creates a wider distance within the increasing number of n. You see over here, maybe like this one is x equal to y, and this one is this one is y equal to x. This one is y equal to x square, x quadratic or x power, etc. Power 3, etc. X cubic. So it will go over here. This one we call this little o. And the contrary, little omega is over here. It will create, well, does it mean that it will always constant over here? Well, not necessary. Maybe if we zoom out this one, it has a little bit movement over here. But in the grand picture, we see the bird eye of the chart. We can see over here, little omega is much lower than the Fn and big omega also. So if there is an equation like this, is n squared is an element of a set of little omega? Well, actually, all of the value, etc., it's the function. It's an element of a set. So in set theory, it's easier to explain it through set theory. So it's an element of little o and n cubic. We just need to calculate it, n square, n cubic, and we delete. So we delete n square over here. It's only 1, and over here it will be n, and we put the limit infinity. 1 divided by infinity. Well, it's not really equal, but it's more equivalent with 0. So that's proven. That's how you prove asymptotic notation of whether little. Well, this one is little o. And actually, I will have this question. Prove 8n plus 8. Prove that 8n plus 8 is an element of little o n squared. So by applying in here, try to prove it. I will give you 5 minutes. The first answer will get the point. Oh, sorry. It's 8n, sorry. It's not. I put the wrong, I put something. Yes, this one. Please raise hand if you have already finished the computation. Actually, it's not difficult. 1 minute.
Can it be seen, sir?
Yes.
Okay. So I think, I do believe that the question is like it's n to limit n to the infinite. So
Yes.
For L, there's a hint that we should use L'Hospital's rule. So the L'Hospital's rule said that we do, what's the English? The turunan of both
differentiation.
The differentiation of both the upper part of the fraction, the upper part and the bottom part. So after we get the differentiation of both of them, which is 8 and 2n, we just substitute them. We substitute the infinite to the n. So based on that, we get the answer to 0.
Okay, that's good question. Thank you Putu for your answer. Yes, that's correct. This one is the correct answer. For others, is there any question about this this equation? So we can use orbital rules. Actually, I prefer to say it by the original name orbital rules by Guillaume Orbital. By if you have a limit of something, then you can the limit of the differentiation of the function will be least likely it's equivalent, so we can use it, and it's proven. Okay, thank you, Putu. So 1 point for today. Okay, we'll wait others, and let us continue. And this one is little omega asymptotic notation. As you can see over here, while the limit ends near to zero, near infinity, it will be in here it's 0, and in here it has to be infinity. So that's it. So like the inverse of the little o. And prove that 3n plus 6 is an element of little omega of 1. Let's say over here this one. And we can see over here 3n plus n is fn, and gn is equal to 1. So we apply fn, gn, and over here we apply infinite. Then infinite divided by 1 is equal to infinity. So that's the justification. Also for any c, we can get any c, any constant, we can get n0 for this inequality. It means over here. So that's this one. This is the 0 less than or equal to cgn and less than fn. As we can see, the constant gn is less than fn. Then it's equal something like this. We replace gn and fn with 1 and 3n plus 6. So that's correct. That's the correct answer. For as you can see over here, this one is important. Why? Without n0, without understanding or stating that there is n0, well, if you compute over here, it will give it's not correct. So it's proved for n starting from n0 and after. That's little omega, easy. In the real case, well, in general, we don't explain it. We don't use it oftenly for little omega and little o. Even with the big omega and big theta, it's not as most widely used as the big O. So okay, like this. This is the course. And asymptotic notation. If you see in the book, sorry. You can see over here, it's congruent. This one is congruent It's more likely the size and the dimensional or geometrical shape is congruent with the f. Fn is equal to big O Gn. What does it mean? It means it congruent to f less or equal to G, etc. And for big omega, well, because this is upper bound and this is lower bound, and this is the exact bound. There is no exact bound. This is the actual bound, and this is less. This is very widely, very wide distance. So it's less than, and this one is more than. And well, this is I stated previously. Fn equal to big O Gn actually means Fn is an element of a set of big O Gn. So this one is a set, and this one Fn is a subset of no, not subset. Sorry, subset is different. It's an element, not subset. Element of big O Gn. Okay, that's all. Is there any question so far? Okay, easy to understand. I hope that you don't get sleepy when you hear my voice. Well, because at 1 p.m. and the course is quite difficult. Not well. Some people found it very interesting, but some people found it a little bit difficult. And then after lunch, etc., sleepy time.
Izin bertanya, Pak.
Silakan.
PowerPoint-nya akan dibagikan atau enggak ya, Pak?
For this PowerPoint, you have to pay for it. No. I will share it later, but let me check first because in here there is some source code. Well, maybe I will delete the source code.
Baik, Pak.
Okay, thank you, Clifton. Yeah, I remember, I think last week I didn't share any. Do I share something? Did I share something? Let me check over here. Yes, I just added this morning or this afternoon. And well, I will put over here later. Okay, so we continue over here. For standard notation and common function, I will start firstly with this one. It's very important to understand. You see over here when you compute the computation time, or when you solve problem, sometimes you will find this kind of equation. So we can simplify this equation. Okay, this one is equal to 1 plus a power I, which is this one is 1, 0, and 1, and 2, etc. to n. This one is equal to 1 minus a power n plus 1 divided by 1 minus a. I think it's better to remember this kind of equation. Geometric equation exhibit for exponential growth. As you can see over here, this one is exponential. Remember, it's exponential, not quadratic, not cubic. Well, quadratic and cubic is an element or is part of an element of exponential, but exponential is not only that. Arithmetic progression. This one is another thing. You see over here, 1, 2, 3, etc. What does it mean? It means that it's equal. If we want to compute the total value of this one, it will be n squared plus n divided by 2. This is like the common equation. And this is the representation. This one is for this one, and this one is for the second one, arithmetic progression. Wait, is there? Well, another thing is summation, sum. This one, sum. Random assertion sort is to determine the nested loop over here. Correspond to summation. Over here, you see over here the nested loop. This one and this one, the looping. G minus 1 is big O, this one, because this is the length of A, and of course this is the maximum is A, so we can say it's N square summation. And this is how you prove by induction. I think I don't want to explain this one because you have already studied this comprehensively in mathematical discrete. We have to define the basis, the inductive steps, and this is this one you will provide, or you will have the you have to prove in the this one, the property, or this one, the rule, etc. So you can prove by induction. Okay, so we jump to the book. Maybe you can open it also. This one I already provided through this one, growth and function. And we'll continue to this one, asymptotic notation. Sorry, not this one. Growth function. Where is growth function? This is transitivity, comparing function, many of relational properties. Well, this one is more like theoretical foundation. And I don't think this one is well, it's not, it's rarely used or rarely discussed in the general context, of course. So we'll start with this one, standard notation and common function for the second chapter. Continuing this one. Do we need to calculate? No. Okay. This section reviews some standard mathematical function and notation and explores the relationship among them. It also illustrates the use of asymptotic notation. In this course, or in this subchapter, it explains about the standard notation and common function, and it will be used widely for solving problems in your daily activities. Well, before daily activities in SPUG, in the online chat, etc. First one is monotonicity. A function fn is monotonically increasing. It's not constant increasing, but monotonically increasing. So it tends to increase. If I can draw maybe something like this. You see, the increasing is not it's not standard, or whether it can be in constant way, or maybe it's like the no, sorry. No. Something like this. So m, sorry, let me close. If m less than or equal n implies that function m is less than or equal function n. Similarly, it monotonically decreasing. It's if m less than or equal to n implies that function m is greater or equal to fn. This is decreasing. function fn is strictly increasing if this one strictly increasing, and this one is strictly decreasing. Next, we have floor and ceilings. I think it's in senior high school we got this course. Well, for me, it's more than 10 years or 10 years ago, more than that. For any real number x, we denote the greatest integer less than or equal to x by, this one is the floor of x. We read it the floor of x, and the least integer greater than or equal to x by ceiling of x. See, like this one is like lower bound, this one is upper bound. But no, it's different. Lower bound, upper bound, the term is used to explain. In this case, in this course is for the notation, but in this case is ceiling and floor. So in here, the example for all real x minus 1 is less than or equal the floor of x. You see, real x, what does it mean? It means that something like this. Let's say x is how much? 3.56. So the ceiling will be 3, and no, sorry, ceiling. Floor is 3 and ceiling it would be 4. .56 minus 1 is less than the floor of x, and less than or equal to 3, and less than less than or equal to ceiling of x, and greater than less than or equal to x plus 1. As you can see over here, 356 etc. minus 1, 256, and plus 1 is 456. Okay, I think it's easy. I think it's more interesting if we have a case study because we'll be more active. For any integer n, this one is the example. Other example, in the real number with the floor and ceiling. It's monotonically increasing as is the ceiling function. This one. So both the floor function and ceiling function, normally it's monotonic. Well, it's not normally. It's obviously monotonically increasing. If the value of x it's increased, so it will increase also. So we have floor, we have monotonicity, and here we have modular arithmetic. For any integer a and any positive integer n. Okay, I remember. Before we continue, but this one, let us visit the course of this one, this problem. Yes, this one. RFG. Let me share the link for you, because I think there is it's not directly, it's indirect relation, but it's good for you. So this is the first assignment for this week. Try to open this link and try to solve the problem. Well, try to understand the problem. I will give you like 5 or 10 minutes to understand the problem. Then we'll discuss it shortly. Then we'll continue to solve the problem. Okay. Is there any question? No. It's a little bit difficult, more difficult than last week. Not yet? Okay.
Cepatlah sampaikan kepadaku agar ku tak berharap membuat kau bersedih. Bila nanti saatnya telah tiba, ku ingin kau menjadi istriku. Berjalan bersamamu dalam teriknya hujan, berlarian ke sana kemari dan tertawa. Namun bila saat berpisah telah tiba, izinkan ku menjaga dirimu, berdua menikmati peluk.
If you see that for every number k which has an m of 0 here, we can see that 4 is, let's say, 1 plus 2 equals 3, and then 3 equals 6. Because 6 is more than 4, and 1 plus 2 equals 3. Let's say this way. 1 plus 2 equals 3, 1 plus 2 plus 3 equals 6. So we have this number 3 and 6, which is 4
which 4 is located in between. Like 4 is more than 3, but it's less than 6. So 4 is have a n value of 3, and to count the m, we just have to count 4 minus 3 minus 1. 3, no, that's not what I meant. 4 minus 3 minus 1. So no, that's not what I meant. Sorry.
So you can change the format.
What I meant to say is like 3, which is 1 plus 2 is less than 4.
Yeah.
So if we subtract 3 from 4, we got 1. And then we subtract 1 from that, we get 0. So say if the number k is 5, so that will be 1 plus 2 is 3. 1 plus 2 plus 3 is 6. So we got these numbers here. So the n would be 3. And the m would be 5 minus 3 minus 1, which is 1. Is that the correct answer? Yes. I think that's correct, sir.
Yeah, that's good. Yes, actually, that's a good answer how to get the m and n. But for n, I think how you get n, for example, let's say the number of k is 10.
10 would be 1 plus 2 plus 3 plus 4. This, I think this is 10. Yes, this is 10. So 10 would be, because this is equal, oh yeah, I forgot about that one. 6. Wait, I need to count this first. I need to, so that will be 4. From
Okay, that's
0,
good.
1, 2, 3, 4. Hey, 3. So 10 would be 4, but then oh yeah, this number
Yes, continue.
in that case, I think.
But in this case, you
Oh.
you calculate it manually for the n.
Oh, I think for 10, we need to find a number that is because 10 is equal to 10. We don't use 4. We still in 3. We are still in 3. So n would be 3, and m is 10 minus 6 minus 1, which I think still works.
Can you try the can you try to type the formula? Because actually, yeah, that's nearly the correct answer.
Perhaps we can use factorials, but
no, we don't need to use it. We don't need to use factorial.
No.
Actually, we can use arithmetic function that I explained just before the slide.
Oh, okay.
But it's fine. Just show us how to find m in the formula. If let's say if you know the value of n and if you know the value of k.
If I know the value of n and k, so let's go back to this case here.
Yeah.
We got 10 as k. So the n is 3.
No, it's 4.
It's 4. Oh yeah, it's 4. It's 4. Sorry.
Okay.
All right. So it's the n is 4, and if we count 1 plus 1 plus 3, we got 6, right? So m would be 10 minus 6 minus 1, which is 4 minus 1, which is 3. That's what I found. I didn't
Try to
know how
type it. You work in Excel, right? You can
Yes.
type the formula, maybe.
Formula for m
Yes.
is k minus n minus 1. I think this is it.
It's factorial? No, I don't think it's factorial. You see, factorial is multiplication.
Yes, I see. That's not right.
It's the arithmetic progression.
Yes. We just type AP here. It's okay.
Yeah.
Okay.
Okay. Well, that's nearly correct. Well, I think you can stop for here. Maybe other. Is there any other person want to explain? Thank you, Sidki, before. That's good. Yes, Nabil, please.
Mungkin
Your brute force. Yeah, arithmetic progression.
Kita lewati kurang di lah. Terus
Okay. Okay, thank you, Nabil, for your opinion. Yeah, that's good also. Actually, the answer. Wait, let me. Is there any other opinion? Other candidates? No. Okay. So this is the moment of truth. No, I just want to give you the hint. Wait, let me check first. Keep it okay. Let's go. So if you mention, well, if you notice my explanation previously in quick math review, you will see over here there are two. The first one is geometric progression, which is widely used for exponential growth, and the second one is arithmetic progression, which is widely used for the arithmetic, the plus, etc. And in this case, luckily, we apply it directly. So it's like something. Let me wait. Well, this one actually something like this. And plus 1. That's better. Similar to this one. And let's go visiting this one. So firstly, we'll understand, so other students will understand also. Consider the sequence of all integers that can be represented as 2 power by m plus 2 power by n for integers 0 less than or equal to m and less than n in increasing order. So this one is monotonically monotonically increasing. Given a positive integer k, your task is to find m and n for the kth element of the sequence. The input, the first line is an integer t, is the number of test cases, which is normal, widely used. T lines follow each line contains one integer k is the math requirement. It means that this one is the sequence number, which is from sorry, I think it's from where? From 1 until 10 powered by 9. And the output is for its test case in the two numbers m. You see over here, the rule is m less than n. It's represented by the sequence number k. So if we have 3, for example, 3 case study, 1, 3, 5, and the output would be 0, 1, 1, 2, 1, 3. What does it mean? It means we can represent it like this. This one. So, okay, thank you. If you see with Ivan, I think. Yeah, Ivan Muhammad Nizar, for your first explanation about this. Yes, you are correct. This is how we represent KMN, and this is the function. So 2 power by m plus 2 power by n over here. And this is the k, this is the informed. If 1, you see over here, 1 and the number of m is 0 and n is 1. And for 3, it's 1 and 2. And for 5, it's 1 and 3. As you can see over here, there is some pattern. You see, m is always less than n and starting from 0. So n 2 starting from 0, this one starting then plus 1, 3. So we have occurrence. This one 1 only 1, 2 we have 2, 3 we have 3, 4 we have 4, etc. Yeah. For a moment, we don't consider this first. Okay, just forget it first. So, how to solve it after we know the representation, after we understand? Actually, I will take into account the approach of seed key to find m. Well, you can try it later. You see over here, we will use the sailing. This one we will use sailing, so to define the number of firstly we have to find n, and n over here with this pattern we firstly the k, as you can see k over here. This is the n plus 1. This is arithmetic progression. Then we can move it like this. We make a quadratic equation. Persamaan quadratic, polynomial quadratic. This one n square. You see n square plus n divided by 2. So 2 multiplied by k. Then we move k to over here, or we move n square and no, we don't. We move k over here, so we got 0. Actually, 0 over here equal to n square plus n minus 2k. After that, we will find the root of the quadratic equation. You remember Cedar High School? Or maybe in calculus, sorry, it's not this one. Let me close this one. Which is this one. You remember this equation? It helps a lot. For engineering it helps a lot. So we will use this one, and we consider only positive non-negative integer. which is we consider only the positive value of x. X in here is n. So that's why I applied over here -1. So let us see over here. This one is A. Remember, this one is A, B, and C. A plus B and plus C. So we take A over here, B, sorry, minus B. So -1 plus the square root of B square, which is 1. 1 minus 4 multiplied by A. What is A? A is 1 multiplied by C. Say, what is C? C is 2 multiplied by 4, which is 4 minus 2, sorry. So this one would be plus 8 and K. We left K, because we have K over here. So in this case, I apply K over here. Okay, after that, well, we divided by 2 and we calculate. So we got this answer, like the root square, the root of quadratic function, this one. And we can apply, as you remember, the current course, this one, there are floor and ceiling. So we'll consider the ceiling. As you can see over here, we take the ceiling. So I just apply ceiling over here in Excel to find out the number of n. By doing this, we will get n, obviously. And that's a good thing. So 4.2 is actually the ceiling of 4.2 is 5, 4.4, etc. And we'll compare over here. So it has the same value. You see this one and this one. That's how you get n. Is it clear for you? I think it's easy to implement in source code. Well, for m, well, I will leave it to you. But actually, the approach of Sidki is nearly, it's very good. Well, in here I will share the code. This code comes from Mr. Sulaiman. So this is the application of to finding n. Sorry. And this is we use, what is it? It's like R. Well, let's say it's in the name of the variable R. N square. Firstly, we have to apply arithmetic progression. Yes, Sidki has a pointer for that. Then we not k minus this one directly, but we have to add n plus k minus this one. By doing this, we will get the correct answer of m. So it's easy, right? But to find this one, you need to understand, or you need to remember a lot of things. Okay. Is there any question? Well, I will share the code. I will share this this code also. Or is there any one of you which still found it difficult to understand? Let me know. If there is a problem, well, as usual, I would like to ask no. I will give you another assignment. This one you don't need to. Well, you can submit it. Of course, it's good as practice. But I will give you another assignment, which is this one we will discuss next week. So I will give you this. So try to do this one. Well, later. I'll give you the information later. We'll continue with this one. Why we discuss about the case study? I want to show you that the equation over here, the common function, etc. It's important and it's practically useful for the problem at the minimum in online chats, and of course in the real problem of engineering, we'll use it. So we arrive at force and sailing previously also. Monotonically increasing, and we apply result arithmetic progression. This one is the following is modular arithmetic. For any integer a and any positive integer n, the value a mod n is the remainder or residue of the quotient a divided by n. It's normal. You have understand in your basic programming class. It follows that this one, yes, it's so if a equal to n, it will be 0. This one, a equivalent to be modulo. I think it's clear for you. So we continue with polynomial. Well, actually, it's a little bit my domain. It's my domain in machine learning, and currently I'm focusing on creating regression formula by using polynomial. For example, for predicting confirmed case of COVID-19, etc. It's very useful, and for me, it has a good performance if we have a good tuning. So polynomial given a non-negative integer d, a polynomial. Sorry, this is not variable. A polynomial in n of degree d is a function of Pn of the form something like this. So starting from 0, it's more like something. Can I write here? As you remember previously, n square plus n plus minus 2k. So I starting from 0. Actually, this one is n but power 0. And it's not actually it's not for quadratic function, etc. It's equal to 0, but for polynomial it's not 0, of course, so that we can get the result. So as you can see, ai over here is 2k, and n power 0 is here. Actually minus 2k. Okay. And some with n over here, then over here is 1, and some also this one, and square a over here is 1 also. This is polynomial. Where the constant a0, a1 until ad are coefficient. Well, normally, maybe you learn polynomial or quadratic or cubic, the power 3, power 4, but actually it's polynomial. It can be like power 6, power 7. It depends on the purpose, and the more value of higher value of d, the more complex it can shape, or the more complex it can be built. The chart or etc. the result. Coefficient of polynomial and ad is not equal to 0. A polynomial is asymptotically positive, and if and only if ad is positive. It's not non-negative, but it's positive. So positive polynomial infinity we have, and we have Bn theta and t. As you can see over here, we consider only the highest order term. We don't consider, and we neglect the, well, we ignore the constant of the highest a over here and the lower term, the lower order term for the computation. We say that a function fn is polynomially bounded if fn big O and k for some constant k. This is for certain case constant k. Okay. Well, k over here is similar to t. And the next we have exponential. I think it's like a revisit of your senior high school, but in this case you apply it in programming cases and online chats, of course. So the exponential for all real a more than 0, m and n, we have the following identities. A0 equal to 1, of course, whatever power 0 is equal to 1. A power 1 is a minus 1 is a per 1 per a. Mn is, well, this is a review of exponential computation. It's equivalent like something like this. And this one em plus n. For all n and a positive, normally it's integer. But well, actually it doesn't need to be integer, real. It can be real, but it's more than, greater than or equal to 1. Monotonically increasing in n. So maybe if you want to draw n square, something like this, n cubic, something like this. And when you draw n, something like this. For all, we can relate the rates of growth of polynomials and exponential by the following fact. Okay, so this is the growth of polynomial and exponential. Well, you can apply it. It's useful. So for all real constant a and b, such that a more than 1 and b equals 0, from which you can conclude that. So this is first, and this exponential function base with a base strictly greater than 1 grows faster than any polynomial. Any exponential, this is important, any exponential function with base strictly greater than 1 grows faster than any polynomial function. So if you have, for example, sir, let me type here. So for polynomial, we have like 2n power by 10 plus n, etc. For exponential, normally we have what? We have 2 power n. Let's say for a it's 2 or whatever the number. You see over here, don't distract, pay attention sometime, because I think this one is like, this one is more is higher than this exponential. Yes, it is for a less than 1, but if a more than 1, this one n and b, if n and b greater than 1, then exponential is growing faster. So if you find out complexity exponential and polynomial, try to choose the polynomial first. It's very interesting in this case, not only for this computation, how to compute in this online chat, but in real case, we applied also in, for example, confirmed case of COVID-19. Maybe you remember in April 2020 or well, April or in March, a lot of people try to figure it out how the pattern of confirmed case will grow. And some people or some articles write that it will grow like in exponential way, or it grows like yeah, it's in exponential way. Actually, I found out a lot of people say that it's very faster. The growing and the growth of confirmed cases very fast. But for me, I try to compare it with the polynomial, and I use it. It's also another approach like Weibull distribution, and well, some cases of nonlinear regression I applied, and I compared it also with linear regression. And the result is that it's far from exponential. So if you say that the confirmed case growing rate will be like exponential, you are absolutely wrong. Whether you are still sorry, whether if the people say that whether they are still dummy in data science or machine learning or some kind of mathematical formulation, or they don't understand really the problem or how to represent it correctly. So it's not really exponential. Why? Because at the end there is a limit, there is an inflection point, and the growing rate it's not as exponential as not really exponential, but it applies non-linear regression, but it's not really an exponential. You can plot it better with polynomial, and you can apply it other methods also, but not exponential. That's how we apply it. And okay, sigmoid function also. Sigmoid is good. By doing this, you can find the S shape. You see, the confirmed case of COVID-19 is always in as a sigmoid shape, because it has the limit of population of humans, so it's not in exponential. Okay. Well, exponential partially correct, in the middle lower. Okay, that's all comparison about the exponential and polynomial. We return to the course. Using E, you see this one is natural number. You will find a lot of cases, natural logarithm function. You will find a lot of useful purpose of E over here. This one, E power by X. Well, you may remember this one. It's useful. This one is, I think it's Euler number. We call it Euler number. Yeah, but Euler is 1. Leonhard Euler. So this one, okay. Euler number, natural logarithmic function. And this is factorial, so it's widely known for you, hopefully. And this one is, let me see. This one, for all x n, n is equal to logarithmic, this one, natural logarithmic function, x. And then after that, we have logarithmic. LG, you see LG, actually there is a It will be differences between LG and LN, learn. Pay attention if you use LG, especially if you use the current tool or something, because LG is like log2 n binary logarithm, which is used to calculate in divide and conquer. Merge sort is one of them, one of the approach. And ln n is the log Euler number, this one n, natural logarithm. Log k exponentiation, and log is composition. And after that we have like log 10, etc. An important intentional convention we shall adopt that logarithm function will apply only to the next term in the formula. So I think we will continue this next week. We still have factorials. Well, I will stop right here. Why? Because for logarithmic and factorial, we have to understand deeply how we convert, for example, this one. How we convert from power to log, etc. We have to review it again. Why? Because it's important to calculate the computation time of divide and conquer approach. We have factorials. What do we have in another functional iteration? The Fibonacci number, etc. Okay, that's all. I think that. Okay. So we'll visit again to this course. For this one, I'd like to ask you, just try to read it and we will discuss it next week. Or wait, let me check. Yeah. Or this one, let me open. Previously, I found the case number. Do you have any questions so far? Well, I'm typing. Is it clear or it's difficult to understand?
Izin bertanya, Pak.
Silakan.
Berarti yang tadi itu dicoba aja ya, Pak. Nanti dibahas minggu depan. Berarti bukan dikumpulin kayak lalu.
Wait a minute. Actually, I prefer to apply the same pattern as Mr. Sulaiman, because this one is tugas kelas. Actually, it's 1 day task which you have to finish it today. But for me it's too complicated. I think for you it's complicated to solve it today, as I understand. So you'll focus on this too, but understand it more comprehensively, more comprehensive. Sorry. This one, yeah, thinking backward and divisible by 8. So the task is still the same. Let me copy from here. Let me check assignment. Let me change this one. New lesson, no, don't do that. Okay, the deadline is next week. So next week 00, which is 30 March 23.60 0.59. So you only have to do these two. Thinking backward and divisible by 8. Well, you can start it right now. If you have any question, etc., you can ask me by through WhatsApp group, etc. Is it clear? Okay. Well, actually, that's that kind of answer is Indonesian way to speak English. I mean, like Asian way. In Singapore, we use you see there is an accent in Singapore, etc. And like Indonesia, we just like answering instead of using English culture, we use like Indonesian but in English. Like apakah sudah jelas? Jelas. That's the Indonesian culture. But in English, we don't. Normal. I think I don't think we see we say that is it clear? Clear, something like this. Well, it's fine. It's good. It's how to say? It's a joke. It's fine. It's good. I found it funny. Okay, thank you very much for your attendance and for your participation. Let me know if you have any difficulties. And tetap jaga kesehatan. Semoga segera divaksin. Selamat sore. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih, Pak.
Thank you so much, sir.